All right. Hey, how's it going, guys? You saw these diagrams in class today, and you noticed that we had some similar triangles in these diagrams. So now it's time for us to sort what the heck this is all about. That's right. Let's learn all about these relationships that were identified in class today. Of course, we have the blue line segments. They relate to the red line segments in a certain way. It's actually something called geometric mean. That's what we're going to talk about today, shall we? You're going to be dealing with those diagrams today in just a second, so this will definitely have to do with shapes. But the big thing about this section is that it's going to introduce a definition for you of a certain mathematical calculation that comes up a lot in geometry, because as we notice in geometry, we have a lot of proportional relationships. Now, this is a particularly special proportional relationship called geometric mean. So maybe pause the video right now. I'm gonna go through this video kind of quickly just to save kind of time, so you're not looking at like an hour and 10-minute long video. So maybe pause the video and make sure you copy this in your notes. You're really trying to understand what this definition is saying, and really try to bond with it when you're actually writing it down in your notebooks here. If R, S, and T are positive numbers, okay, so we're gonna give you a formula. If we're giving you variables like that that are undefined here, this is going to be a formula for us to kind of use going forward. R, S, and T are positive numbers, and the following is true. Then S is called what will be called the geometric mean between R and S. That number S is a geometric mean between R and S if the following is true. Okay, so I know what you're thinking. In this actual proportion, remember, in proportions we have 4 terms. So remember, this is term 1, this is term 2, this is term 3, this is term 4. And do you remember what the means? Guys, do you remember what the means were of a proportion? Yeah, that's right. The means are the ones kind of in the middle. That word mean is going to take away a different meaning in a second, because we'll see that these means here are actually between these two extremes. We'll see it in that one here. And there we go. We have it right there. This is the geometric mean. So if we only have 3 of these numbers and one is the geometric mean of the other two, this is how you set it up right here. Okay, we have 3 numbers. One of those numbers is the geometric mean of the other two. This proportion is true. What that's telling us, right, if this is given to us here, this number is the geometric mean of 2 numbers here, the following proportion would be true. That one number to the geometric mean is the same thing as the geometric mean to another number, okay? So it's sort of like, what is the number that's sort of wedged in between 2 other numbers? Proportionally. That's kind of what a geometric mean is here. Here's the official definition. Here's how you're going to work with it, right, in the actual proportion right here. R to S equals S to T, right? Those means are the same, right, across this diagonal. That's where your means are, terms 2 and terms 3. So let's look at it a little bit more practically here, because sometimes it's easier to look at actual numbers rather than have to deal with variables right away. So I wanted to show you a couple of examples, really easy examples of noticing when we actually do have proportions set up in such a manner where we can actually see a certain number is a geometric mean, not to be confused with the way that you've been calculating means in the past. How have you guys been calculating means in the past? You probably had to do that in some middle school math, right? Calculate the mean of these 2 numbers, for instance. We'll get to that in a second. But a geometric mean is the sort of proportional mean here. So let's look at this one right here. 2 is the geometric mean between 1 and 4, because 1 over 2 is the same ratio as 2 over 4. We'll look at that in the next slide. Here, 6 is the geometric mean between 2 and 18. If I said 18 over 6, that's the same thing as 6 over 2. Right? They would both simplify, right? 18 divided by 6 is 3. 6 divided by 2 is 3. Thus, 6 has got to be the geometric mean of 18 and 2. Any 2 numbers, right? Any 2 numbers will have a geometric mean, and that will simply involve solving. Okay, simply involves solving. And you might have to use means extremes property. We'll see it in a second, actually solving for a geometric mean. All right, next thing up here, because I sort of teased it a second ago here. That word mean you've probably heard in middle school math, right? We talked about finding the mean between numbers and whatnot. So this is just another way to find kind of some middle numbers here, right? The mean kind of means middle numbers if you have a set of numbers. What you guys have been calculating in the past, when you hear the word mean, and when you hear the word mean in the future, say you're taking AP stats and it says calculate the mean of this thing, they're going to be talking about something called the arithmetic mean. Mean, average. How do you calculate average? Well, if you have a set of numbers, you would add all those numbers up to one another, add the whole set of numbers. You add each one together, and then you divide by the amount of numbers that were in that set, right, to find the average of that set, okay? So comparing geometric mean can be for more numbers. It's a little more complicated, but we're just going to be worried about geometric mean for 2 numbers. So I'm going to compare that to the arithmetic mean of two numbers here. All right, here we already looked at this one right now. 2 is the geometric mean between 1 and 4 because the following proportion is true. If I have 1 over x, I'm sort of giving you a heads up here of how you solve for a geometric mean. All right, got two numbers, 1 and 4. What's the geometric mean? Okay, so I know that my means are the same, right? Because it's what number makes that proportion the same, right? Makes it work. And that's going to be 1 over 2, right? 1 over 2 is a half. 2 over 4 is a half as well, right? They're both 0.5. Okay, so that's the geometric mean between 1 and 4. Notice here, the way you've calculated mean in the past, add the two numbers together and then divide by what? Well, how many numbers do you have? So divide by 2. This is the arithmetic mean. Let's look at the arithmetic mean between 1 and 4. Is it 2 also? Let's check it out. Well, we'd have to do this as our equation here. 1 plus 4, add both numbers together, divide by 2. We're not going to really be doing this from geometry. I just want to show you this is how you calculated mean in the past. But what that's called is the arithmetic mean, not arithmetic, arithmetic. 1 plus 4, add them together, divide by 2, you would get 2.5. So notice here, the mean, the geometric means between those two, it's got to be between those two numbers. The arithmetic mean is also between those two numbers, but it's just calculated a little bit differently. One person has $1 and another person has $4. On average, you'd have $2.5 per person, right? $2.5 per person. How'd you get that? 1 plus 4 divided by 2, that's 2.5, $2.50. But if one person has $1, another person has $4, proportionally, the proportional relationship would be, well, I want somebody who has twice as much money as the person who has $1, and that person who has $4 has twice as much money as that. So there's kind of this common ratio, right? Common multiplier between these here. 1 times 2 is 2. 2 times 2 is 4. So it's a little bit different, right? If you're phrasing it a little bit differently, it's sort of like, well, it's sort of in terms of a common ratio, right? So if you have one person with $1, person with $4, you want one person who has twice as much as the lower, and that to be twice as much gets you to 4. The answer would be 2, right? 1 times 2 equals $2. $2 times 2 is $4. So it's just a different way of kind of calculating an average, right? There are a lot of different ways we calculate averages and centers in math. Could be arithmetic mean, could be geometric mean, could be something called the median. So you're learning about geometric mean this time around here in geometry, because this comes up proportional relationships. Of course, coming out of chapter 5, we know it comes up with a lot in geometry. All right, here are just some more examples here. 6 is the geometric mean between 2 and 18. I don't need to spend much time on this. Boom. We already talked about it in the last slide. This is true, but I just want to show you this is how you solve something like this, okay? And here, 10 is the arithmetic mean between 2 and 18 because here we go. 18 plus 2 over 2, right? That's going to equal 10, okay? 18 plus 2 is 20 divided by 2 equals 10, okay? You with me? You with me? I know these videos are kind of long. Hope you stay with me here. I'd be able to do this in class just fine, but anyways, let's move the video now. Okay, so just one thing to point out here. Notice here, the arithmetic mean, this is just an observation. This might come up later. The measure of center, that's the arithmetic mean, is actually always going to be higher than the geometric mean. 10 is still between, right? 18 and 2. 6 is between 2 and 18, but the arithmetic mean is a little bit higher, okay? Let me go back to this here. Say, guys, because you're going to have to do this in the very next slide, actually. Say you're asked to find the geometric mean. We don't know it's 6 yet, right? Find the geometric mean between 2 and 18. Between any two numbers, there's going to be a geometric mean. There's going to be that one value that's going to be able to create that common ratio, and set up that proportion with us here. This is how you do that, right? Just set up your means. Your means are unknown, but what do we know about geometric mean? They're going to be the same. Right? They're going to be the same. The means are going to be the same here, okay? So how do you solve a problem like this? Maybe start thinking about that because you're going to have to do that in the next slide. Well, what I would do is this, and what you should do is cross multiply. That's right, cross multiply. Use the means and extremes property. My extremes here are 18 and 2. Multiply my extremes together. My means are x and x. Multiply my means together. 18 times 2 is 36. X times x is x squared. Oh, I have a quadratic equation. I know that because my x is being squared right here, but it's an easy one to solve because I can solve this quadratic by doing what to both sides? I have x squared here. How do I isolate x? I got to take the square root at both sides, okay? So you guys are definitely be taking square roots here. Okay, so geometric mean is defined as positive values, okay? So this is, you might remember from Algebra 1, if I'm doing this here, I got two solutions for x. X could either be -6 or +6. But if you were paying attention to the last slide here, a geometric mean is always a positive value. It's just defined for positive integers here. So even though I'm doing the square root of 36 here and the square root here, normally I'd have to put a plus or minus in front of this because x could either be -6 or +6, right? -6 times -6 would also be 36. But because geometric mean is just defined for positive values, here, there's your geometric mean right here. It's got to be 6. 18 to 6 is the same as 6 to 2. That's how you're going to solve these algebraically. So go ahead and pause the video in a second, because what I'm going to do is drop this in. Now you try, find the geometric mean between the given numbers. That's right. You have 2 practice problems. Ready, set, go. Get on it, get on it, get on it. Not sure what to do? Then watch my example on the last one. I just did one for you. Set it up. We don't know the means, but we know the extremes. Find the geometric mean. 15 seconds. Three, two, and one. Mr. Fortin's just going to do it, and maybe I'll talk about it afterwards here. Check out how I would do this.
Here is the dome. Back with the bass, pajamas live in effect, and I don't waste time on the mic with a dope rhyme. Jump to the rhythm, jump to the rhythm, jump. And I'm here to combine beats and lyrics to make you shake your pants, take a chance. Come on and dance.
All right, let me pause right there for a second, and hopefully you got the same thing I got. Again, geometric mean going to be the same. So 3 to 4.58, about 4.58 is about the same as 4.5827. They're about the same decimal, right? They're about the same number. Common ratio and same proportion. So cross multiply, get x squared. Cross multiply here, get 21. Square root of 21. Cool. That's actually a simplified radical expression. We're going to deal with that next class, as a matter of fact. If I took the square root of that and sort of got it as a decimal, I might round it 2 decimal places. 4.5 is what I got here. Here, this one's a little bit more interesting. This is a little bit of a preview of Wednesday's class. This is actually something that I could simplify a little bit here. I'll show you how to do that in a second. But here, same thing too. Set up the means, the unknown means here, right? The means are the same. This is a geometric mean. So we got to find the freaking common ratio here, and with the same numbers as our means here. So 6 to about the square root of 90 to square root of 90 over 15. So I cross multiplied there, and then I took the square root. And so I could have done that on my calculator and gotten a decimal. I'm going to show you something else right now, though. That we're going to deal with next class. So I got about 9.5. What we're going to do next class is something called simplifying radicals. Yeah, simplifying square roots here. So look forward to that. We got to do that before we do Pythagorean theorem, because there'll be a lot of practice of that coming up here. I can break up here. 90 actually is the same thing as 9 times 10. Right? You should be with me there on that one. That's the composite, one of the composite ways we can show 90. So 9 times by 10. That's the same thing here too. The reason why I show this is because actually 90, square root of 90, we can simplify that because 90 has a perfect square factor. Okay, 9 is a perfect square, meaning we could take the square root of this one. What's the square root of 9? It's 3. Okay, 3. So technically, I want to show you this. 3 times by the square root of 10 is actually the most simplified way we can write our answer in radical form. You should have learned radical form a little bit when you did quadratic formula last semester, but perhaps you forgot. This is one way to simplify that. I think I did a little bit of simplification last year here. So this could be that, or it could be about 9.5. All right, let's go to the next slide here, because why is geometric mean important? It's going to come up in the diagrams that we saw in our freaking class today. So hopefully you saw it, hopefully you got through with your group. There's our diagram right here. It's more official, kind of coming up in the textbook here, but this is the same diagram we had in class, but this is the one in the textbook here. So geometric mean will come up in diagrams like this, where they show 3 similar triangles. So question for you, you should have maybe observed this with your groups in class, but maybe you had trouble seeing it. Can you spot those 3 similar triangles? Well, can you spot those 3 similar triangles? Well, here, even though we only see 2 right angle symbols, are there any more right angles, for instance? Because these 3 triangles, these 3 similar triangles, we're going to prove that they're similar by AA. That's going to be the way, right? So we're given the angles here. There's a different congruent. So UNT is definitely congruent to SUT, those 2 angles. Is there a third angle, though? Oh, yeah, of course, right? So a right angle, if a line's perpendicular to another line, then it creates 4 right angles, right? So this is a right angle right here, right? This is a right angle right here, too. So this little guy, right, this little triangle, we have this sort of medium triangle, and I'll call this guy that starts at the beginning, we'll call that the large triangle right here. They're all similar to each other by AA. Okay, so there is the right angle. We need to figure out what the other angles are. We can maybe talk about it later. So we'll talk about this in a second. We're going to use this to prove it, but here is your correspondence. Here is your similarity statement right here. And look at this here. Actually, angle S corresponds to angle S. So interesting. There's only one angle S in the diagram. Huh. Wait, so you're telling me that angle And the right angle here might be congruent to that angle. It might be congruent to itself. And that right angle up there, oh, interesting. Okay, so SNU similar to SUT by AA. And that's the first one there. Yeah. I think we might see how this works out. We're still going to go through the proof, though. So we have this right here. Okay, pause this for a second. Take this down in your notes. This is a theorem. Okay, what does it do, right? This is a good true-false question. Like, if an altitude is drawn to the hypotenuse of a triangle, what does it do? Fill in the blank. Might be a good fill in the blank question here. So let's go ahead and draw that altitude. So I do it this way because I don't want this diagram to be too kind of overwhelming for you at the beginning. It might have been overwhelming in class, but if we just pair this back here, we can do this with any right triangle. Right? We can do this with any right triangle. We start with a right triangle, and that right triangle, we can find 3 similar right triangles simply by constructing a perpendicular right there, which would be known as the altitude to the hypotenuse. So this is only true when we're coming from the right angle to the hypotenuse at a right angle, right? That's an altitude, right? Remember, an altitude is drawing a line segment from a vertex of the triangle that's perpendicular to the line containing the opposite side. So if you're doing that from the right angle, it's going to hit the hypotenuse. So if an altitude is drawn to the hypotenuse of a right triangle, what we're going to prove in a second here, and what you observed in class, I'm hoping, is that the 2 triangles that get formed, okay, I already kind of talked about a second ago, SNU is going to be similar to SUT, but SNU is also similar to UNT, okay, because we'd have SNU is congruent to UNT, the angles. And then they share an angle too, don't they? No, they don't share an angle. Oh, how does this one work? Okay. Oh, this is pretty interesting. We might have to have kind of a go-between, an intermediary similarity thing here, right? One is going to be similar to another, and then that one's similar to yet another one. So there might be some transitivity in this proof. I know, because I wrote this proof. We have it here. So this is what we're going to do. We're going to do this one right here to prove this theorem for you. Hopefully you added this one to your notes. Now we're going to prove it. We don't have to actually write the steps out on the proof. We'll just hopefully follow along. Hopefully you'll get it here. All right, step 1, state the givens here. We got a triangle SUT with a right angle there, and this is our altitude. Okay, this is our altitude. We know this kind of definition of an altitude. An altitude is drawn from that right angle perpendicular to the hypotenuse, as described by kind of the theorem here. That's going to be helpful because we're going to prove these triangles congruent by AA. What's maybe the angles we'll talk about first? Maybe we should talk about the right angles. How many right angles are there? There are 3 of them. What do we know about right angles? They all measure 90 degrees. That's my first statement right here. Because we're given this as perpendicular right here, okay, we'll use the definition of this to say that UNT and UNS have to be right angles. And the definition of right angle, what do we know about right angles? Well, they measure 90 degrees. So we can say that, right, we have a right angle at SUT too, so definition of right angle, SUT is 90 degrees, but also definition of perpendicular, definition of right angle, those are also 90 degrees. So they all equal each other. So there's my one angle that I can check off the list to get some AA similarities between the 2 triangles. What about the other angles? Well, angle S is in the smallest triangle. Angle S is also one of the 3 angles in the largest triangle. Angle T is an angle in the medium triangle. What other triangle is angle T a part of? What triangle? The largest triangle here, okay? So what we need to say now to get this into AA, remember we only have 1 pair of angles that we've already stated are congruent to one another. We need to get a second one prior to asserting that the triangles are similar by AA. So we're going to say this. We're just going to simply do reflexive. Remember, if an angle is in more than 1 triangle, right? Because triangles are overlapping, that's why diagrams like this are kind of hard to see and kind of hard to work with. Then we might as well say that they're congruent to themselves, right? To themselves, because then that makes it closer to proving a congruency or a similarity here. So we have angle S congruent to angle S. We have angle T is congruent to angle T, and this gets us to get some similarity statements. Can only do it for 2 of the triangles so far. Check it out here. So we know that these are all 90 degrees. So that's all fine and dandy. But here we just said angle S. So angle S is in SNU. It's in SUT. So SNU and SUT must be similar by AA because angle S is in both of those triangles here. This is SNU, that's the small guy. SUT is the largest guy. But we also said that that right angle is congruent to that right angle, right? We did that in step 2. We said the measurements are equal. That's good enough, right? That's good enough here. So good to go there, AA. We also said angle T. So now we had our angle T1, UNT, which is the middle one, and SUT. So here, look, I've talked about SUT twice. Okay, SUT is similar to 2 other triangles through AA, right? Angle T is congruent to itself, reflexive, and we'd already said that that right angle and that right angle both measure 90 degrees. So they're congruent too, right? So now we said that those are similar. Is that the theorem though, guys? Have I actually proved everything? Have I proved this statement up here that those two triangles that were created are similar to one another and the original triangle where we drew the altitude? No, I haven't said that yet. All I've said is that the small triangle here, I've said this in this top part of the statement, the small triangle is similar to the largest triangle, and the medium triangle is similar to the longest triangle. That's what I've said. I haven't actually said what. I haven't said that the medium and smallest ones are similar to one another. But how can I do that? That's right. Similarity is an equivalence relation, right? So similarity gets the reflexive property of similarity, symmetric property of similarity, and of course, transitive property of similarity, which is the one that I'm using here. SNU, triangle SNU is similar to triangle SUT, but I also know triangle SUT, the largest triangles, similar to the medium triangle. That means the smallest and medium must be similar to one another. Okay, so we did a transitive property of similarity a bit earlier in chapter 5, chapter 5, because it helped us prove some things here. Okay, so it hasn't gotten crazy yet, right? Class hasn't actually really gotten crazy. What have we done? Defined the definition of geometric mean, practiced some problems, and also went into that diagram that I remembered in class today. I said, tattoo this to your arm, right? That should be a geometry tattoo. You're gonna have to deal with a diagram like this quite a bit. I'm looking forward to it this week. So get a tattoo of it, get used to working with them, because we're going to have to work with them now, because we're going to get some theorems in a second. But just wanted to point out here that before we actually have these theorems, we can potentially use the fact that we have 3 similar triangles to prove some things already, to be able to deduce stuff about side lengths. But we might move more slowly than we would if we didn't know the other theorems that we're leading to. So anyways, what I'm trying to say is right now, you could actually solve for this. You can figure out what H is, okay? You can figure out what H is. Why can I figure out what H is? Well, I know that here, it's a different triangle, but of course, look at this here. My premises are filled with the situation. So we have here a right triangle, okay, where an altitude's drawn in. Here's my altitude, okay, here's my altitude. So I know that I have this triangle here, SUX, is similar to UTX. So, right, the smallest triangle and the medium triangle are similar to one another. That means we're going to have some correspondences here. What do we notice about H in the blue diagram? H is actually the longer leg of the right triangle. What do we know about H in this other triangle right here? It's the shorter leg of this red right triangle that we have on this side here. Why is that relevant? Well, we know that we have a similarity statement right here, so they don't actually correspond to one another, but this longer leg right here is going to correspond to this longer leg of this triangle it is similar to, right? We're just coming out of this in chapter 5, the similarity chapter here. So this longer leg here, H, goes to this longer leg here, which is 9, and this shorter leg here, 4, would correspond to this shorter leg of the red triangle over here, the medium-sized triangle, which is H as well. So guys, we're going to have a geometric mean right here when I set up my proportion. So we could solve this. We could figure out what H is via similarity. We're going to get to it as a theorem because you want to be able to solve something like this very quickly without actually like looking at triangles to figure out what's going on here. You're going to want to know the altitudes of the hypotenuse of a right triangle is going to be the geometric mean between that and that. Let's make sure we understand this one here. Okay, so check this one out. This is the longer leg right here. This is 9, so maybe I'll start with that. 9 to the longer leg of the blue triangle. They correspond, right? Because it's corresponding sides of similar triangles are proportional to one another. So that ratio 9 to H is going to be the same as, again, we're starting with the red. The red's on top here. Medium triangle's on top. H to 4. Okay, H to 4. And so check it out here. H is the geometric mean between 9 and 4. Okay, 9 and 4 here. Do our little trick. H times H, that's H squared. Ooh, 9 times 4, that's really easy. That's 36. Take the square root of both sides. H has to be 6. We found ourselves. We found our altitude right there. And that's going to be our first theorem. Let's get into it. First corollary, actually. We already had a theorem, this one here. But this is following from the fact that we have similar, right? We have 3 similar triangles. And when you have those 3 similar triangles like this, because you have an altitude drawn to the hypotenuse of a right triangle, that's the first thing I wanted to write out here. Maybe I wrote out the whole thing. No, I didn't write out the whole thing. No, I did. Altitude's drawn to the hypotenuse of a right triangle, the length of that altitude. H right here, geomean, between 9 and 4. Right, between 9 and 4, which I just slowly showed for you here, but we want to get quick at this. You're going to have this tattoo solve problems like this pretty quickly in time. So let's make sure we understand what's going on here. Again, we're geometric mean, we should have 3 components in this here. right? 3 components in our proportion. We have the length of the altitude. That's our geometric mean. So H goes in our geometric mean position. And then it's geometric mean between the segments of the hypotenuse. That's a little bit confusing. So maybe, hopefully you remember the way I set up the diagram here, right? I had 9 and 4 here because 4, that goes to the smaller side of SXU, right? Goes to H. And 9 goes to the longer side because that's the longer leg of that triangle. It goes to H here, which is the longer leg of UXT. Okay, so the H, it was in both of my ratios in the last one here. That's the geometric mean. The length of the altitude, geometric mean between the segments of the hypotenuse. Take a second, make sure you understand what that statement means, the segments of the hypotenuse. What does that mean? Well, that's not defined for you here, but you have a hypotenuse and the altitude's being drawn to it, that where that altitude hits the hypotenuse, you have segment 1 over here, you have segment 2 over there, and those two things together, geometric mean of that is going to be that altitude here, okay? So if I actually had to set this up, not using H, 9, and 4, I would do it like this, okay? So check this out here. What I mean by the segments of the hypotenuse are segment SX and segment XT, okay? The geometric mean of this is UX. And one thing I wanted you to notice right now at this point here is, again, what is a mean? What does arithmetic mean? What does mean measuring? Means measuring some sort of an average of some sort here, okay? So check this one out here. One way to double check you set up your proportion right is that SX clearly longer than UX. XT clearly shorter than UX. So UX is kind of this proportional average of these two different segments right here. UX is our geometric mean because that's the altitude. That segment 1, segment 2 of the hypotenuse, that's sort of what is being used to calculate the geometric mean of those two lengths. Does that make sense? I don't know. We'll get some more practice a little bit later. Let's do it again. I know this video might end up being a little bit longer. I apologize for that for Monday because I know that you guys have a lot of work on Monday here, but this one says find the length of A. So perhaps we should do that too using similarity because we're going to want to work our ways to getting our theorem here. What I notice about A is that A, what no longer matters here about side length A, that triangle no longer matters about side length A if I were to solve it here. So what I would care about is this triangle over here, which I will call the medium triangle, okay? Medium triangle right here. A is that's the hypotenuse of it, okay? Hypotenuse of it. That smaller triangle over here is not going to matter because the thing that this triangle is similar to that also has A in it is the largest triangle, okay? So if you were to solve for A, you want to solve, like at this point before you have the second corollary, you would do this triangle here to the largest triangle right here. That's how we're going to set up our ratios. There's your hypotenuse of the black triangle, right? The one that's on the left side here, the medium triangle. And that's the hypotenuse here. And here, this says H. That's not going to help us at all because H is the altitude of the larger triangle. Remember, that's similar to, that also has A here. So we want to maybe go to this 9 here. So I'm going to label this one up here. This is the longer leg, okay? Long leg of this black triangle right here. We're going to set up a ratio. Maybe I'll start setting it up right now. Okay, so let's set this one up right here. We'll do 9, and I'll put A right here because that's the hypotenuse of this black triangle. That's going to relate to this larger triangle right here, which is red. Sorry, this isn't red. This is cyan. Hi, cyan. This is going to relate to the hypotenuse, okay, which is 13. Check this one out here. Hypotenuse. So the corresponding sides of similar triangles here, you have the hypotenuse of the middle. If we're trying to find A here, that's the hypotenuse of the medium-sized triangle. That would be in the same ratio to the hypotenuse of the largest triangle as 9 is, which is the longer leg of the black triangle, to A, right? Check it out here. This is definitely the longer leg of the largest triangle in the diagram, the one where we initially drew the altitude to here. So this is the long leg. So part A is both a hypotenuse and a longer leg, and that's why we can, in two different triangles, and that's the reason why it's going to end up being a geometric mean here. 9, which is the longer leg in the medium triangle, to A, which is the longer leg in the largest triangle, that would be a scale factor, right? A scale factor here. Same scale factor would be A, which is in the black triangle, right, is the hypotenuse, to 13, right, which is the hypotenuse of the largest triangle. There is your scale factor, small to large here, okay? So A is the geometric mean between 9 and 13, and I will solve for that now. see, 90 plus 27 is 117. 117, I don't think we're simplifying that at all. Kind of have to take the square. Maybe write a decimal in that one, or just leave it like this. Let's see. Actually, wait a second. 9 goes into that. Wait a second. 9 goes into that. What am I thinking about? Yeah, this is 9 right here. So 9 would definitely go into 117. So I can actually simplify this one here. That would be, yeah, again, square root of 9 times 13, right? We just did that. So if I were to actually simplify my radicals, we'll have a lesson on this on Wednesday. Square root of 9 is 3. And square root of 13, that's a prime number, so there's no square to that. So 3 root 13, that's what actually A would represent here, simplified as possible, okay? So let's look at another one here. It says find B. This is getting kind of messy, so maybe I'll clear that out. So if we're gonna get B here too, a similar argument can be made. All right, we got that triangle. It's gonna be similar to the largest triangle of the diagram right here. What is B in terms of this red triangle over here? Well, that's the hypotenuse. Hypotenuse is right here. Again, we don't care about this H, this side length H here, the longer leg of this, because that has nothing to do with the large triangle here, which is the one we're going to use similarity to solve for B. B is not a part of this triangle, so we don't care about this left triangle. We just care about the large one here. So we're going to label this one up here. This is our shorter side, and we're going to compare it to the largest triangle, which again, they're similar to one another, right? Which we proved a second ago to get us to these corollaries. The corollaries are the important things of this one. It's going to allow us to move quickly through problems, right? You want to get these formulas and be able to move quickly through problems and understand where they came from. Okay, hypotenuse, there we go, 13. We also care about the shorter leg here. Shorter leg is, yep, there we go, it's B of the green triangle. Okay, so that means that we're going to have B down here and B up here, because we're going to do our scale factor small to large, and to be consistent, because we know that we have a consistent scale factor because the two triangles are similar to one another. And small to large, well, B is the shorter leg here, so we need to look at the shorter leg of this one. That's 4. Okay, 4 to B and B to 13. And that is, my friends, that is the geometric mean of 4 and 13. So check it out here. So to sort of summarize, US is the geometric mean between SX and ST. The one we're looking at right now, UT is the geometric mean, right, the B right here, of XT and 13. Let's figure out how we can maybe word that out on the next slide. So we get B squared equaling the square root of 4 times by 13. What do I know about 4? 4 is actually a perfect square. I can take the square root of 4, and that's 2 or negative 2, but I just care about the positives here because my geometric mean needs to be a positive number based on our definition, so 2 root 13. Okay, I get a decimal of that if I wanted to, but that's a more precise answer, is the actual square root number there. All right, so let's get to it, guys. Let's get to it. So I tried to show this to you, right? I tried to show you in class. I know it's kind of hard to really follow all this stuff here. Here's the corollary. So as long as you have this corollary kind of memorized, and kind of know what to do with it right away, you can solve problems like these very quickly. And they are puzzles, right? You're not going to get all of them right away. You'll have to, kind of review it on the Jamboard and make sure you're persistent with trying to get it right. So check this one out here. When the altitude is drawn to the hypotenuse of a right triangle, each leg is the geometric mean between the hypotenuse and the segment of the hypotenuse that is adjacent to the leg of the hypotenuse here. So if we're going to look at this one here, each leg, we're going to look at 10 here. What do we know about 10? 10 is a hypotenuse of the smaller triangle, but it's also the smallest leg here of the largest triangle. So what do we know is that in the smallest triangle, it's x. We have x to 10 would equal 10 to 25, okay? Because 10 is both a hypotenuse and it's a shortest leg. Look at that, x to 10, short legs corresponds, 10 to 25, largest sides corresponds, or hypotenuses correspond here, okay? What do we know about this one here? What do we know about QP, or y, right? It's equal to y if we're to solve for that one here. Well, y is the geometric mean because it's a hypotenuse of the middle triangle. It's also the longer leg of the largest triangle here. It's hard to keep this all set in your head, right? These are puzzles. These are supposed to be challenging, thought-provoking. It's supposed to keep you up at night. So we have here longer leg to this longer leg here, right, to YP, okay? So we could set this up as YP, or we can make this, YP is technically should be 25 minus X, right? You're gonna have to do that here. If you're actually solving this one, get Y here, you'd have to do 25 minus X to Y is the same as Y to 25. That might be one way to start a problem like that here, okay? So let's maybe check that out and go back here, make sure I got it right. Given this, right, when our situation, our premises here, we're given that we have an altitude, right triangle right there. We know that we have similar, 3 similar triangles what we can set up here and deduce is that, well, each leg is going to be the geometric mean of the segment of the hypotenuse that it's adjacent to, and the whole hypotenuse itself. So what does that mean for 10? X to 10 is going to be the same as 10 to 25, right? That's how you're going to solve for this one here. What does that mean for Y? What does that mean for that other leg? Well, Y, okay, it's the hard thing here is to keep track of everything you need to kind of set up these ratios accurately here. Y is the geometric mean between the part that's adjacent to it on the original hypotenuse and the whole original hypotenuse of that triangle that we drew the altitude to its hypotenuse of. Very confusing, but I think I said it right there here. Okay, so we know that if we're thinking about if we're going small to large, right? Small guy here, this is the hypotenuse, so it would be 25 over Y. And then now we're going large to small. The large is the lower leg, so it would be Y over 25 minus X. I think that's our answer here. I think I did it wrong. I think I wrote it down there wrong. I think that's incorrect. Is that incorrect? I think that's incorrect. Well, it doesn't really matter, actually. Technically, it doesn't really matter because that would just be the inverses of the other thing here. Anyways, I'm going to keep moving on here because we got to keep moving. Okay, this is going to be on your exit ticket. So I'm going to go over it with you guys here in case you struggle with it, in case I need to take it back to you, be like, hey, just watch the video, find the values of X, Y, and Z. Well, hopefully you have some ideas in doing this. Let's see if we can get X here. Well, X is our hypotenuse. I think we have to save that for the end. Let's maybe look at Z first. Okay, Z is the altitude. Okay, Z is the altitude to the hypotenuse, it looks like here. So it's the geometric mean of this and this, right? Of the two segments of the hypotenuse. So you want to start by looking at your largest triangle and figuring out where the hypotenuse is here. Okay, here's our hypotenuse. That means 2, and whatever that is, Z is the geometric mean of that. The problem is, do we know what this is here? No, but we know that we could create an algebraic expression for this. Okay, if this whole length is X and this is 2 of that whole length, then we got to take away 2 away from that X to represent what that must equal here. Now we can get up and solve this one. So to get Z here, this would be, Z is the geometric mean of X minus 2 and 2. So let's check it out here. X minus 2 over 2 equals 2. Wait, hold on, Z, I did it wrong. Z. Let me get it back here. So let's get it back here. Clamp this down for a second ago. Okay. Z is the geometric mean of X minus 2 and 2. So I actually wouldn't start by solving for Z first, because then you're going to have 2 variables. You're going to have Z and you're going to have X. So let's maybe see if we can figure out one where we're only going to have 1 variable. Okay, this problem here is a little bit trickier, and maybe you're going to struggle with this on the exit ticket, so hopefully you're watching this here. So I wouldn't do Z is the geometric mean of X minus 2 and 2. That's 2 variables. You're not going to be able to solve that. So let's start looking at the other sides here. Y is the geometric mean of what? Well, of X minus 2 and X. Again, that doesn't really help us. We have 2 variables. So what do you have to do in a problem like this? Maybe look at the last one and see if there's going to only be 1 variable in this proportion. So let's check it out here. This leg, okay, so this is a leg of the original right triangle, and that's the geometric mean of, well, 2, the segment of the hypotenuse that this leg is adjacent to, and the whole hypotenuse here. Okay, so 6 is the geometric mean of X and 2. Starting off with a hard problem on your exit ticket. But this problem you could actually solve for. You can get this one here. Look, check it out here. 2 times by X, that's 2X. 6 times 6, 36. And hopefully you followed my logic here. Divide both sides by 2, X equals 18. So there we have 18 right there for X. Okay? What's Y? Can we get Y right now? Well, I can't get Y right now. Well, actually, no, never mind. What am I doing here? That's not 18. This is 6, right? This is 6 right here. I got X equals 18. That's going to help me because, you know what? There is my hypotenuse. My hypotenuse here is 18. You with me? It's kind of confusing. I can't believe I'm giving you this problem. I can't believe it's going on so long. But here, my hypotenuse is 18 here. What do I know about this now? It's no longer X minus 2, or it is X minus 2, but I might as well say what X minus 2 is. X minus 2 must be 16 here. Okay, so this segment of the hypotenuse is 16. That segment there is 2. So it looks like I can actually get Y. Y, this original leg of the largest triangle, is the geometric mean of the segment of the hypotenuse it's adjacent to and the hypotenuse itself, the original triangle's hypotenuse. There's a lot going on here. That's why you practice, okay? So this cross multiply, get Y squared, right? 36 is just 6 squared, so I got that there. y squared, and then I have 16 times 18. So I'll go to my calculator and get this. Oops. 16 times 18. And I get 288. Is that a perfect square? No, it's not, but it's actually pretty close to a perfect square. So we got here 288. So what I'll tell my TAs to look for is just, you got to take the square root of both sides to get this here. I might tell them to look for square root of 288, and that's fine. But we're going to work on actually simplifying this next class on Wednesday. And the way you do this here is this is 288. I just happen to know if I divide 288 by 2, I get 144. Because I've studied this a lot, I know that 144 is actually a perfect square, right? 144, if I divide that by 12, I get 12, right? So if I do this here, so I divide this by 2, okay, right? Because this is 288 is the same thing as 2 times 144. So 2 times 144, well, this is 144. 144 is a perfect square. I take the square root of it, I get 12. So technically, the best answer you can have here is 12 times by the square root of 2. That's the most simplified way you can write the length of y, okay? 12 root 2, okay? 12 root 2. So, z. We could have gotten z last time. That might have been a little bit easier. Z is the geometric mean between the two segments of the hypotenuse. Notice here, the leg, we just use one segment of the hypotenuse, and then the whole hypotenuse itself. This other leg, we use that segment of the hypotenuse, and then the whole hypotenuse itself. So 2 parts of the hypotenuse, but not both segments. Both segments of the hypotenuse, that's for the altitude, reserved for that. So you're always going to have 2 parts of the hypotenuse. Either it's the whole thing, or it's going to be one of the segments. The altitude gets both of the segments of the hypotenuse here. And that's what it's the geometric mean of here. Okay, so set it up in the mean position, we have z's. And it's the geometric mean between 2 and 16. Is this one we're going to be able to do in our head? Well, let's see here. 2 to 8. Now, I don't think there's going to be a way we can do this in our head here. So this is going to be z squared equals 32. Okay, take the square root of both sides. I'm going to tell my TA to look out for this. Square root of 32 on your exit ticket. Okay, what we're going to do on Wednesday is simplifying square roots here. 32, is there a perfect square that goes into 32? Sure, 4 goes into 32. That's a perfect square. There's a better one than that. 16 goes into 32. What's the square root of 16? It's 4. So in this one here, it's going to be square root of 16 times by 2. Take the square root of 16, that's 4. Z equals 4 root 2. Okay, so I'll probably have my TA send you this video in case you don't have 12 root 2, don't have 4 root 2, or you can have the simplified one. That's fine too. Or you don't have 18. Those are the 3 ones you gotta look for. Hopefully you followed that. And that's it. We finally got there, but check your answers, make sure it makes sense. Just all right, there you go. You're going to write down something like this on your exit ticket. I'm sorry so much work on Monday, but a lot less work on Wednesday. We're going to simplify radicals that day. So anyways, we want to get this out here because this is definitely a similarity. Is your mind melting? Is mine melting? I know mine is. Here, you're going to have to do a diagram kind of like this in your notes for the exit ticket. So maybe you can hold off on that, but just want to show you these are the things visually you're going to have to keep track of here. I know the altitude, it's the geometric mean of the 2 segments of the hypotenuse, of this and this. I know one of the legs, it's the geometric mean of the segment of the hypotenuse that's adjacent to that one in blue and the whole hypotenuse itself. The same thing can be said for that leg of the right triangle. It is the geometric mean of that segment of the hypotenuse, the one where the altitude hits and it goes over to the endpoints that's shared with that leg and the whole hypotenuse itself here. Boom, that is true. Boom, that is true. And finally, last but certainly not least, boom, that is true. That's all I got. Thanks for watching. Thank you for taking your notes. Example problem set. We're not going to do this one. It'll be slightly different on Tuesday. But this is normally where I dismiss and be like, have fun with that for homework. We'll review next class. See you later, guys. Bye.